Benjamin Good will be presenting both tools. Ben received his bachelor's in cognitive science at UCSD, his master's in evolutionary and adaptive systems at the University of Sussex, and his PhD in bioinformatics at the University of British Columbia. He's worked with Andrew Su on GeneWiki project since 2010, first as a postdoc at GNF and then at TSRI. And as of November 2014, Ben is an assistant professor of the Department of Molecular and Experimental Medicine at TSRI. His first presentation will be about Mark2Cure, which aims to apply crowdsourcing to the challenge of extracting structured information from text. Without further ado, allow me to introduce Ben.
Hi, can you hear me okay?
Yep.
Can you hear me? Yep. Okay, so I'm actually going to go in reverse order and tell this more as a contiguous story that begins with the GeneWiki and ends with Mark2Cure, but I will pause in between those two segments for any GeneWiki specific questions. And so let me, without further ado, let me get going. Let's see if I can. Okay, so the challenge that we work on in our lab and on these two projects in particular is to make biomedical knowledge more organized, accessible, and computable. As anyone knows, we have a lot of it, and it's growing at a rate of more than 1 million articles a year, and so it's an increasingly acute problem. Our strategy in this lab focuses on crowdsourcing, and it focuses on this idea of the long tail. This is a slide that if you've seen Andrew present, you've probably seen before. But the idea here is that of the long tail is that traditionally you would have a few people making a lot of content. For example, a few people writing newspaper articles write a lot of content individually. And nowadays, in the long tail phenomenon, you have many people making little smaller chunks of content, but which in aggregate can actually be quite a bit more than can be produced by a few. And you see this phenomenon sort of across the internet now. You can compare, the production of movies with TV and Hollywood versus YouTube, and so on and so forth. And so what we're trying to do is take advantage of that phenomenon in bioinformatics. And so this is the idea of community content curation. So this is a Nature article that came out in 2008, where basically the biocuration community themselves, the creators of the gene ontology and so forth, basically said that it would be impossible to go about doing the amount of biocuration that's necessary given the traditional path forward, basically of the short head. And so basically sooner or later, the research community, broadly speaking, will need to be involved in the annotation effort to scale up to the rate of data generation. So that's our challenge. And so that brings us to the two arms of this presentation and our work. And like I said, I'm going to start with the GeneWiki, so we'll swap the ones that have been suggested. So GeneWiki. So here is the point of the GeneWiki. The idea is to filter, extract, and summarize the content that's in PubMed to make it easily accessible. So when you search for an article about a gene, or search for articles about a gene, like this one, you will get a lot of results. And over time, that number is only going in one direction, right? And so rather than having to scan through them yourselves and do all of the sort of interpretation yourself, what we want to do is translate that result list into a review article that you can consume quickly and easily to get information you need. The way, of course, we do this is through some computers and a lot of crowdsourcing to move from the space of a sort of infinite pile of documents to the space of discrete articles about concepts, specifically about concepts of genes. To make this work, so this is a great idea. I mean, a lot of people tried to do this around that time that this got started, but most of them didn't work. To get a wiki running, you need to generate a positive feedback loop. It begins with some initial amount of utility. So there needs to be something to get the ball rolling. From that initial utility, some people will find the content on the internet and it will get used. That's the idea. from those people, a very small fraction of them will become contributors and make that content better. That will increase that content's utility, its value, which should increase the number of users, which should continue to increase the number of contributors, and everything goes well, you get a phenomenon like what happened to generate Wikipedia itself. So that's the goal. So where are we with respect to the goal? This project began around 2008 with the creation of these stubs articles in Wikipedia, which speaks to the idea of that initial utility. This is an automatically generated view for Wikipedia. All of this is coming in via what they call bots. They're just little programs coming from a variety of structured databases, including EntreGene, the PDB, the Gene Ontology, and so forth. So this is what you get when you say, okay, I want a GeneWiki article. So that's the initial content that we use to attract people to create a review article. And moving to the next arm of our little positive feedback loop, we've done a lot of studies measuring how well we're doing. And so in terms of users, the GeneWiki is viewed more than 4 million times per month, and this has been consistent over the last several years, and it only basically steadily increasing. One of the reasons that the whole thing works is Google. If you search for a gene, you're very likely to end up with the GeneWiki page as one of your first or second hits, if not in the top 10. And that really drives the whole process, of course. And then from that large number of users, which is what we really benefit from being in the Wikipedia environment, we have a consistent number of editors. So across any given month, you'll have more than 1,000 edits with an increase of more than 10,000 words. So a few years ago, we basically estimated that the content in the GeneWiki would approximate between 200 and 300 full-length scientific articles, all of which created, for free. And so these articles range dramatically in their individual sort of value, from the initial stub articles that I showed you, which do have value, at least as resources for linking off to other places, to articles like this one, which we like to show as an example of what can be achieved here. This is an article about Relin. You show it's organized into 11 different major sections with all kinds of subsections. You can have any kind of content you want in here, pretty much, images and videos and so forth. You'll find all of them in this article. From one of the most important things to know about Wikipedia, if you don't already, is that they have a very strict requirement for referencing. And so any of the GeneWiki articles, any sentence that makes a statement in there should be associated with some original article, generally linked back to PubMed. And so that's one of the most powerful features of it. And of course, we have hyperlinks off to related concepts. To give you a feeling for what goes into building a good article, so this article has been edited by more than 100 people now, probably more than 1,000 times. These stats are a little bit out of date. And so it can really work. That's basically what we're trying to say here. So that's a process that has been going on for quite a few years now. So really initiated in 2008 or 2015 now, so almost 7 years. It's running along fine by itself. We've had consistent growth in content throughout that time, but we wanted to push it harder. So basically there are a number of articles in there where we know there is a lot of content available about that gene in PubMed, but we don't yet have anyone volunteering to write the article. So in 2013 we started a collaboration with the journal Gene, so that we could give people an incentive a traditional incentive to write that content. So the basic idea here in our little deal is that the authors are invited to write a review article for a gene that's not well represented in the GeneWiki. They get an official publication, but they're also associated with that review, but they're also required to create or update the corresponding GeneWiki article. So far we've had about 10 of these finished and published. 20 more are in process, and the pipeline looks like it will be expanding rapidly over the next year or so. So that's a nice way to give the community a little push. So, these talks are, marketed as discussions about tools. So if you think about the GeneWiki as a tool, what it is a mechanism for collaboration amongst teams of people working on gene annotations. A lot of people do that. The lesson here, and from what we've seen across the board, is that don't roll your own wiki if you can do the same job in Wikipedia. There's enormous benefits of working in that context, even though it's, frankly, a bit of a technical pain. So that's the message. I have two more of these yellow ones. Look out for those as they come along. So that's the beginning of the GeneWiki, and this is about where I personally came into the story during my postdoc. So all of that free text that's generated is fantastic, and it's a very useful resource on its own, but as bioinformaticians, what we would really like is structured content. So we would like to have, things like gene ontology annotations, disease ontology annotations, and so forth, so we can use them for computation. And one of the things I did, and other people do, of course, is to attempt to do that through text mining, which is a difficult process. And this is my favorite picture to depict what that really means. And so we're working on other ways to go about doing that. So one of the things that we did in the text mining, one of the concepts is that we could mine out annotations, structured annotations, and give them out to other public databases. Like one of the ones that we created was called the GeneWiki Plus. One of the new things that's come on the scene is called Wiki Data. And so Wiki Data is something that is run by the same people that run Wikipedia, the MediaWiki Foundation, and what it's going to allow us to do is change how this all works, so that rather than having our seed articles created by editing wiki pages, we can create them by adding content to Wiki Data, which is a big open public database, and having that displayed in our wiki articles directly. And I'll explain how that works in the next few slides. So the idea behind Wiki Data is to provide a database of the world's knowledge that anyone can edit. It is very much open, and in fact, it's far more open than Wikipedia itself in terms of what you can put in there. The basic unit of representation in Wikidata looks like this. You have a topic like Berlin, for example, just like you would for a wiki page. And then you have claims that are made about that topic. So the claim here is that the population of Berlin, population is the property. It has a value of 3.5 million. It has two qualifiers, it's saying that has that population in this year, given some particular method of estimation. And again, just as in previous Wikipedia, it has a reference to it. And so that claim is encapsulated in something called a statement. And so that's it. That's the fundamental way you represent content in Wikidata. One of the ways that this is immediately useful to them, and one of the reasons why they convinced the Wikimedia Foundation to fund it, is they have this great problem in the Wikipedias of that each Wikipedia is distinct. Each different language Wikipedia is distinct from one another, and it takes a lot of work to manually sync them all together. And so when you're talking about structured data or facts, what you really want to do is have them represented in a sort of language-neutral form that can then be translated off automatically into all of the different Wikipedias. And Wikidata did that. That was its first great success and its first use in Wikipedia. It's actually running live now across Wikipedia and all of them. This is the same across all domains, so you'll see a lot of this content, of course, in geography. And of course, it's the same for us. So here are examples of GeneWiki articles in English, which are articles that we maintain, and GeneWiki articles in another language, which we don't. And you can see they're sort of out of sync. And Wikidata, by moving all of the structured content in Wikidata, we'll be able to do a much better job about keeping everything up to date. So when you're thinking about this, what we view Wikidata as is a bridge between the bioinformatics community globally across all languages and all of the Wikipedias. So to get this going, we had the first step in this process of using Wiki Data within the GeneWiki project was started actually last summer by a Google Summer of Code student, where he took our bot for creating those Wikipedia stub pages and converted them from writing directly to Wikipedia to writing content to Wikidata as a demonstration. And so here's an article, again, our favorite article about Gene, but about Relin, but in Wikidata form. As you'll see, it's complete. It's a database that you're looking at. It's just a view of a database. You can see things about it's the nature of the thing that you're talking about, and then properties hanging off of it, such as regulates or interacts with, and so on and so forth. All of this content is structured and computable and queryable. You can get it as XML or JSON or whatever you like via their API, and their API is increasingly robust, though it is still a work in progress. So on the Wikidata front, right now we can tell you that all human and mouse genes via NCBI gene are now have representations in Wikidata. We did that, and with our initial focus here was on getting them in there and getting all of the identifiers that we could map to them so that we have these initial starting points to hang everything else off of, and to encourage the other members of the community to link up to those central identifiers. We also have all of the diseases in the human disease ontology loaded in there through collaboration with those guys. We're actually working on bringing in all FDA-approved drugs, and from those starting points, we will, over the summer, be loading Wikidata with information that makes connections between genes and diseases, drugs and diseases, and drugs and proteins. And so one of the great benefits of doing this in the context of Wikidata rather than, for example, our own database is that we can immediately benefit from other people doing similar things. So one of the things that happened a few months ago was we noticed offhand that someone else had loaded a bunch of data showing drug-drug interactions, which can immediately link up to our data about these, for example, drug disease interactions. And so that is just what we hope is the beginning of a very interesting, again, kind of positive feedback loop that enabled by Wikidata as a sort of global shared platform for knowledge representation. And so here's the second of our yellow slides on GeneWiki, now GeneWiki Data as a tool. Again, it's the same idea. It's a mechanism for collaboration amongst teams working on representing biomedical data. And again, the lesson here is that if you can do everything in the open, which is the requirement here, don't recreate the wheel. Do it in the open and benefit from the community. So what we've shown in the GeneWiki project is that so far all we're really talking about is the long tail of scientists, and that these folks are valuable sources of information on gene function and on the valuable workers in the process of assembling review articles and structured content. I'm going to take a pause now for any questions on the GeneWiki before I move into Mark2Cure, which will talk about a different population of people.
Yeah, I just have a quick question. How do you track the user statistics if you don't own the pages on GeneWiki?
So there's a third-party tool that gives you page views per article on a day-by-day basis. And you can also, using the API, you can monitor, for any article, you can use the API to ask who's edited it, when they edited it, and that gives you all the edit information.
Okay, thanks. And one other question, can you tell from the statistics, like if the articles are being viewed by the scientific community or maybe like the general public, like the majority of the views, if they're just based on a few genes and maybe those are what are showing up in news stories and those are from the general population?
Yeah, sure. So I mean, when you look at, you know, we're looking at a large article collection, and some of the articles are viewed like a huge number of times, and that is definitely reflected in, and that is driven by the public for sure. So, you know, the EPO gene, the erythropoietin, you know, that comes up a lot, and that's definitely driven by people, you know, watching bike racing and so forth. It's hard for us to know specifically who sees each article, but we can tell. But basically, if you look at the distribution of views, you see this sort of, a few of them have a huge number of views, and then you have this lump where a lot of people are looking at them, and then sort of, again, a long tail of a few people looking at them. And from that, I mean, you can basically guess, just like you're implying, that a lot of the views definitely are driven by a few famous genes looked at by a lot of the general public, but you can also see very clearly a core amount of views by people that would only be looking at this for scientific reasons.
Okay, thank you.
Yeah. And we did, that phenomenon is noted in the first article about GeneWiki. If you want to look at detailed statistics, you look up the article from Andrew and John Huss.
I have a question. So would you be using the Wiki Data to generate the free text in the articles?
So not the free text. So that's an interesting question. So one of the other kind of competitors to the GeneWiki was called Wiki Genes, so very confusingly named. And in that case, they actually went ahead and attempted to create the text of the articles from the structured content that they could get, that they could mine out. And that really didn't get anywhere. And a lot of people sort of suggest to us that we should do more when we're creating a stub to kind of automatically create the articles, which I would have thought was the way to go when I came into this, but it turns out it seems to be detrimental to do that. It seems that people react negatively to computer-generated text in a way that is surprising to me. So on the current game plan is not to do that, is to just populate the info boxes and expand on the info boxes with the content in Wiki Data, and to, again, let the humans write the text. If we get to the point where we can automatically create summaries that are as effective and indistinguishable from human authors, then maybe we'll revisit that as a possibility.
Yeah, that makes sense. Thank you.
Okay, shall I continue?
Yeah,
Go ahead.
yeah, go ahead.
Okay. Okay, so like I said, so the beginning of this, the GeneWiki project was really about scientists. You know, we are trying to get scientists collectively to help annotate genes. You know, the last little bit about the collaboration with the journal Gene is an obvious tip to that, because no one else would care to do that but scientists. But the interesting thing now, of course, is that there are far more people out there in the world that might want to help that are not necessarily scientists themselves. And so the Mark2Cure initiative is a way to reach out to those people to help in this process. And so, again, we're looking at the same problem, this dramatic growth in the amount of content represented as text in the world every year. And the same problem again, it's very hard to query and compute over. So just to give you another flavor for this, aside from this single gene view, what if you wanted to know about how tyrosine kinase inhibitors might relate to hematologic cancer? So you could do that kind of query in PubMed. You get 500 documents out, which is actually not that many. And it turns out it's a small fraction of what you would actually want to get out, because to do that properly, you'd have to expand that initial query to all the drugs that it describes. Same with that initial query about cancer. And you'd want to get all of that content out, and you'd want it represented in a way that you could consume it quickly. Obviously, PubMed is nowhere near achieving that goal. And so what we want to do as our next step here in the GeneWiki project writ large is to extract semantic networks from PubMed, and again, with the crowd's help. So again, we're going from a document. In the beginning, we went from a document to one single article about one concept. Now we want to go from documents to networks of linked concepts. And we're going to do that with some computers and quite a bit of people. And so this process of moving from a bunch of documents, a bunch of text to networks of linked concepts is referred to as information extraction by the computer science community. And you can very broadly and roughly divide into these three things that you need to do. The first being to find the mentions of those high-level concepts in text, like find me the diseases, the genes, and so forth. Map those mentions to specific terms and ontologies. So given that I can tell a piece of text is a gene, give me its entree gene ID. And then finally to identify relationships between those concepts. I'll talk about just the first level, which is where we're at currently with the very young Mark2Cure project. And that's about finding mentions of high-level concepts in text. And so I'm going to describe the results of an experiment that we published in January that was really meant to just prove whether or not, to show whether or not the crowd of non-scientists could interact with biomedical content in a sort of advanced manner that approximates what is done by professionals. So the idea here is all about identifying diseases and symptoms in text. And so what we took as our starting point was a gold standard corpus assembled by a team at NCBI, focuses on text mining. And what it is 793 PubMed abstracts divided into 3 sets, where they had a team of 12 expert annotators create 6,900 disease mentions. And disease does include things like symptoms and groups of diseases and so forth. And the goal of our project will be to try and reproduce what they did with the sort of unwashed masses. So can a group of non-scientists collectively perform concept recognition in biomedical texts? And the way we did this experiment first was using a system called the mechanical Turk. This is something that was created by Amazon. And just to give you an idea about its name, if you're not familiar with this, the mechanical Turk was this automaton from the 1800s. The idea here is that it was magically, like a robot, automatically playing chess at a very high level. And it would actually, this is a real thing that went around and toured Europe at that time and attempted to trick people. Because in fact, what it was a contraption that held a little intelligent man inside of it that was actually playing the game. And this is the idea of what they call artificial intelligence. So you can use the mechanical Turk system to do things that you might think about doing with artificial intelligence programs, and you can make things that behave like that, but under the hood are actually lots of little people. And so the idea, and this is the way this works. So we're the requester over here on the left. We create a bunch of tasks that we want to get done. For each task, we specify a qualification test that workers must pass in order to do it. We say how many people we want to do each task and how much we're willing to pay for that. That's the end of our job. Then Amazon takes over and manages parceling those jobs off to all their worker population, which numbers in somewhere between 100,000 and 1 million, depending on how you look at it, but it's a lot of people, and manages running them through the qualification tests, getting them access to the tasks, paying them, and advertising the tasks. And then they do the jobs, we get the content back. And so it's a very fast way to test out ideas and to get work done by the crowd, the general audience. And so our instructions on this task were as follows in brief. And so the idea was to highlight all diseases and disease abbreviations, to highlight the longest span of text specific to a disease. So this is a tricky one because someone might highlight diabetes mellitus in this case, but of course they would be wrong when we do the analysis because they need to capture the entire string there, insulin-dependent diabetes mellitus. And I point that out just to say that this is actually, although we were seeking a fairly easy thing to start with, it turned out to be a quite non-trivial thing to get people to do. The other aspects of the instructions were to highlight conjunctions as single spans and to also, confusingly, highlight symptoms. So things like dwarfism and learning disabilities and so forth should also be highlighted. All of this is just to match what was done in that gold standard. That was the goal. And so before workers got in there, they had to take a qualification test where they basically had to reproduce these highlights using their survey tool. Once they passed the test, which in our last run about 40% of the people did, they were faced with this pretty simple interface. They could click on the green box to see those instructions. Otherwise, the task was simply to highlight the diseases and abbreviations and so forth. So the task here, and what I'll show you the results from, was to identify disease mentions in 593 abstracts from that corpus. We paid people 6 cents per abstract to do that, and we had 15 people do every abstract, which is no more than you need, but we wanted to see what it looked like. So because we have multiple people doing every abstract, we need to, and that provides an opportunity to do some statistics to decide on what the annotation should be given those 15 different opinions. And so we do this by a very simple voting method. So if you begin at 1 or more votes, you keep all of the annotations from anyone that put them in. So we refer to the vote number as K. So K equals 1. You have very high recall, basically. You get everything in there, but you probably also have lower precision. So maybe you have something like including highlighted and so on and so forth. As you move down the spectrum of increasing votes, you only keep things that have at least 2 people independently annotating them. So as you move from K equals 1 through here, your recall will go down and your precision should go up. And in fact, that's exactly what it does. So the bottom axis here in this chart is the voting threshold K, so starting at 1 and moving out to 15. And described on the y-axis here are 3 different curves, one for precision, which as you can see begins fairly low and moves up to very high to almost perfect. One for recall, which starts out very high, close to 1, and then descends down. And then the F-score, which is basically an integration of those 2 measures. It shows you a sweet spot here at K equals 6, which at F equals 0.87. That number, we think, is actually very close to the theoretical maximum you could achieve, given that the annotation is inherently ambiguous in some cases. And if you look at the levels of agreement among experts, this is actually higher in general than they got amongst each other. And so, based on that information, we can say that in this case, in aggregate, our worker ensemble is faster, cheaper, and as accurate as a single expert annotator for disease concept recognition. And so that was a very well-received study from the biocuration community. I think it opened a lot of people's eyes, including ours, to what could be possible here. And there have been a number of other people doing similar things, and the results seem to be consistent. And if you do this carefully, you can get the crowd writ large to do a good job processing complex biomedical text. And so that's only the first level, of course, finding those mentions of high-level concepts in text. What we want to do, and we have ongoing projects to do, is move forward into the next level, deeper into this, and specifically into relationships. So we want to be able to say, given this fragment of text, identify the gene as we just did with the diseases, and add this to it. So say that, in this case, CDK9 is a therapeutic target for hematologic malignancies. Then we have something very useful and interesting to compute with, and that's a work in progress, making that work. And so I haven't really talked yet about Mark2Cure itself. So that was foundational work to say whether or not it was possible to do this. But we don't really intend, at least at the moment, to do all of PubMed with the mechanical Turk. Although it's actually not as much money as you might think to think about that. So, at 1 million articles a year, if we needed 10 annotators per article, and we had 4 things that we wanted them to do, it's only $2.5 million to do it, all of them. But the question is, could we do it for free? And we think that maybe we could. And so we have the system called Mark2Cure. So finally, I've got to the actual title of the talk now. You can go now and see a website called Mark2Cure.org, where what we're doing is trying to set this up so that volunteers can come in from the community, particularly from patient advocacy groups, people that might walk in a breast cancer walk, for example, and do the same kinds of tasks that we just described on the Mechanical Turk, but do it in a volunteering context. And so we did an initial experiment earlier this year to see how well our volunteers, first of all, could we raise volunteers to do this? Second of all, could they do the job as well as our Mechanical Turk workers? And so we took exactly the same corpus, same job, although we altered the instructions a bit to make it a little easier and less intimidating to people. And we ran the experiment. So we launched this website for citizen science annotation of text on January 19th, stopped it a little 4 weeks later. During that span of time, we had 10,275 individual documents annotated. Again, we went for all the documents redundantly annotated by at least 15 people. More than 200 people participated, and I don't have a slide in this, but I can tell you that it reproduced the AMT results very closely. All the curves look the same. The F measure is within the same range very closely, and the net thing at the bottom there is we paid $0 to do this. And so this is something that we're working hard to expand on now. We have an experiment that's about to launch to identify genes, not only diseases but also genes and drugs and symptoms in scientific articles. So that initial corpus was 500 documents. We are hoping to go after a much bigger one in the second run of actually attempting to do this on 10,000 documents. In addition to that, we have ongoing experiments, as I mentioned, on identifying and verifying relationships in text through crowdsourcing. And so that's Mark2Cure, and this is my final yellow slide. Mark2Cure as a tool. This is something we're working. This is kind of very much a work in progress. So we have a couple use cases that are driving the current experiments, but we're very much seeking additional ones, seeking use cases for information extraction, and collaborators interested in the text mining aspect of this that we could work with. So if anyone has use cases that would be of interest for an information extraction problem, or they have text mining interests, for example, if you're interested in new kinds of data to train algorithms or ways to interact with the crowd, we'd very much like to talk to you. With that, I want to finish by tipping my hat to all the people that made this possible, particularly as Pipe named him the Prince of Crowdsourcing, Andrew Su, who obviously runs all these projects. Mark2Cure is created by Max Nanis, who is taught by Chun-Li Wu. Ginger does all of the work on producing the community for Mark2Cure, which is actually probably the lion's share of the work on a volunteer science project like that. She also manages all of our interactions with the journal Gene. And so I think we're probably one of the few labs that has an official dedicated, what she's called a scientific outreach coordinator. And I think she's vital to everything that we're doing right now. The GeneWiki project has been running for a long time. One of the important people that got it started was John Huss. Eric Clark is now a PhD student at Penn, who also contributed a lot to that, as did, of course, many people in Wikipedia. And we have a large and I'd say rapidly growing team of people working on Wiki Data with us. So with that, I will end and hopefully answer any further questions you have.
Thank you.
Or we'll get some coffee and start our day.
I suppose I have a question. The volunteer version, Mark2Cure, were the people more accurate either on trying to pass the initial test or during the actual annotations of the real material?
So we don't have a comparable test for them. We changed the sort of starting point quite a bit. So I can't tell you that, but the annotations were actually a little bit less accurate overall than they were from the Mechanical Turk group, but they're really close. So the F measure for all of them, Mechanical Turk was 0.87. For the crowd, I think it was 0.84, 0.85 for the volunteers. But there's a lot of things that go into that. I think that one of the things is that we sampled repeatedly from the crowd in Amazon. So basically every time you run an experiment, you can accumulate the email addresses of people that do well on it. And so I think we had a kind of extra selected population there for the last run. But the basic answer to your question is that it's almost identical in terms of what they can do.
Have you considered like some kind of reward system for Mark2Cure? I mean, people love, you know, like Reddit or anything where they get votes and points and that sort of thing.
Yeah, you know, we've gone through all kinds of ideas about that. You know, we've talked about doing, you know, T-shirts and and things like that. And we haven't done it yet. We do have the concept of profile pages in there, so we have places to put that if we decide to go for it. So, you know, give people extra stars or show them, you know, show a high score list and so forth. But one of the reasons we haven't yet is a lot of this work is motivated by a very successful citizen science project called the Galaxy Zoo, which now has branched off to be called the Zooniverse. And they don't do anything like that. They don't do any of the kind of gamification things at all. And the trouble and the difficulty with doing it, although it can obviously work really well, is that if you put in a new incentive, like the incentive is to get a T-shirt or the incentive is to win on the high scoreboard, you have to be really careful about making it so that people can't game the system to maximize their access to that incentive. If you don't do that, if you just say, look, your incentive is to be here to help science, you're much safer from that potential problem. And so it's something that whole line of work is something that I think we'll kind of do as needed as we go forward. We have, I mean, just to give you an idea, the Zooniverse project has more than 1 million people on its mailing list with no gamification on it at all. And so we think that there's probably, and you think about the number of people that, as I mentioned before, will do a walk for breast cancer or a run and so forth. We think that we might not need to do that at all once all the kinks are worked out of the system. That people will basically just there'll be enough people that will be motivated intrinsically just to be part of this community and add their sort of, you know, bit of time to help science, that we won't have to open that can of worms. But if we do, we have lots of ways to do that too. So that'll be unfolding over the next year or so.
Oh, well, it looks like the Zooniverse website is sort of a portal for web-based citizen science because it links to a lot of sub-projects, and they have some in biology.
Yeah.
So have you guys considered like getting on this website or on this mailing list so that?
Yeah, absolutely. I've been in touch with their leader, the Chris Lintott, and I'm trying very hard to get us listed in there. They actually have something very interesting that's starting that may be of interest to other people. It's called Panoptes, so all the projects that you see listed in the Zooniverse there are driven by their same back-end infrastructure, which prior to this thing was closed, so you basically had to be approved by them to use it, and then they did all the work. What the Panoptes system is going to be a publicly available way of putting your own content into that environment. I don't know if you'll officially be listed on their list, but you'll be able to use all their back-end resources. And so at a minimum, we'll be able to use that framework to drive Mark2Cure. And I think it's very likely, based on my conversations with them, that we'll be kind of an official part of the Xeniverse project at some point this year.
Cool.
Yeah, that'll be really exciting to be part of that group.
Okay, are there any other questions for Ben? Okay, if not, this concludes our presentations. Thank you, Ben, for that wonderful presentation. Both tools sound amazing. So next, this concludes our presentations. Next week, we'll have 2 more presentations about PC Quant and Branch. Please tune in next week. But thank you all for attending this week's conference.